Newton's third law. So this is the final law. It's the action-reaction law, which basically states every time we put a force on something, that object will react by putting a force on us. So essentially, you can't push on something without it pushing with a force that is equal in magnitude, but as you can see with this negative sign indicating opposite direction. So if I apply 10 newtons of force in the positive x direction on something, that same object will apply negative 10 newtons of force in the x direction on me. So again, an action would be any applied force, and when two objects come in contact, basically, if we think microscopically what's happening, one surface is pushing on another surface, they're repelling on the microscopic level because of their electrons, and that produces a reaction, and because it's repulsive, it's going to be in the opposite direction. So again, for every action, there is an equal and opposite reaction. We call the process of action-reaction an interaction. Basically, two objects transferring both momentum and transferring energy with one another via these opposing forces. And that'll be very, very important for when we talk about things like conservation of momentum. So we think about different interactions. You tap the keys on your keyboard. As you push down on them, you can actually feel them pushing back on you. You have pressure sensors in your fingers. Basically, these are nerves that sense pressure. You know you're getting a reaction because you can feel that actual pressing of the keyboard. The Earth pulls on the Moon, otherwise the Moon would continue in a straight line, but it orbits the Earth. And likewise, the Moon pulls on the Earth, causing it to wobble on its axis. We can see the most direct effect of this reaction if we watch the tides go up and down, because the Moon pulls on the Earth, but it pulls on it at different strengths, causing the ocean to rise and fall at different places. Of course, everything in our solar system is essentially held together through gravity, primarily the gravity of the sun. But even though the sun pulls on the planets, keeping them in the orbits, the planets themselves cause the sun to wobble on its axis. In fact, this wobble is seen in other stars and has been used to detect the presence of planets which are too dim to see with a telescope. Atoms are held together by the electromagnetic force. The electrons pull on the nucleus pulls on the atom, and even on the nuclear level this holds. For every action between each quark, there's an equal and opposite reaction. Now let's take a very simple case of the starting blocks. Why do we have starting blocks in a foot race? Well, think about how things work here. We want to accelerate quickly. So by Newton's second law, we want the largest force possible, in this case in the positive x direction. So what we do is we push, there's our action, we push backward on the block, and this causes the runner to go forward. It's actually at an angle, so we're actually pushing down and back, and that causes the runner to come out of the blocks, pushing them up and forward. Action-reaction. Again, we look at the form of somebody running. Here we have the action, the force of the foot on the track. The reaction, the track pushes forward and upward. Okay? Analyze all the different forces here. Weight pulls down. The reaction from the track pushes up and forward. If we add these two vectors using the parallelogram method, we see the total force is down the track. We are accelerating down the track by pushing at that angle. Swimming, same thing. Archimedes' principle says the weight of the water displaced is equal to the buoyant force acting on the object. That's action-reaction. If you're in the water and you're displacing water, you're displacing some weight, some force, gravitational force of water. As you push on the water, it's the only thing you're in contact with, the water pushes back on you, pushing you up, giving you buoyancy. So Archimedes' principle was a specific case of Newton's third law even before Newton came along. Propelling yourself through the water, what do? You pull the water past you. As you pull the water past you, you're forcing the water from head to toe. That's your action. The reaction is that the water pushes you forward. And this, in fact, is how you jump. You push down on the floor, okay? And the harder you push down on the floor, the faster this interaction with the floor, the greater the upward velocity and the higher you go. Now, basically, we can use action-reaction to talk about any case where we're propelling an object using thrust. Look at a ship's propeller. It's basically a large wedge which is rotating, which is forcing the water in one direction. Stand behind a boat and you can actually see the water streaming behind the back of the boat, or streaming away from the back of the boat. That is the action. The water, the faster we can propel the water backward, the more reaction we get and the greater the thrust forward. Planes, like the swimmer, demonstrate two distinct directions for action and reaction. First of all, we have the propeller in the front of this plane. The propeller is grabbing on the air and pushing it backward behind the plane. Okay? That is the action. The propeller pushes on the air. The air, therefore, pushes the plane forward. Action, reaction, equal and opposite forces. Additionally, the aerodynamic surfaces on the wings, although you've probably been told with Bernoulli's principle, you get a low pressure on top, a high pressure on the bottom. In actuality, we can look at this in terms of Newton's third law, is as the air is being pushed downward. In fact, if you lower the flaps on the wings, that'll push even more air downward, creating greater lift for a slower speed. So again, action, reaction. Air is pushed down, the plane gets lift, or is pushed upward against the force of gravity. Jet engines just take this to a little more extreme, whereas a propeller airplane, a prop plane like this, is powered by an internal combustion engine, much like an engine you might find in your car. The jet engine is propelled by a continuous influx of fuel, and it's a continuous combustion. The internal combustion in a car is very rapid. It's ignited and then it ends. In a jet, it's continuous, so you can actually get a tremendous amount of force and a tremendous amount of power in a much smaller space. The way it works is you have compressor blades that compress the air, as the name implies. That air is combined with fuel, which is sprayed into the combustion chamber. This combustion reaction heats the gas very rapidly, causing it to expand. It does work on the turbines. The turbines power the compressor blade. And for turbofan engines, they have this additional large blade out front, which pulls additional air past the jet engine. So it's almost like a jet engine powered propeller on this. In fact, many of the higher performance prop planes are actually not powered by internal combustion engines. They're powered by a jet engine, but instead of a turbofan like a conventional commercial jet, the shaft is connected to a much larger prop or propeller, and essentially the principle is the same. The larger prop isn't able to rotate quite as quickly, and because of the geometry of this, there's a limitation to how fast it can go. But again, with these you can go pretty close to the speed of sound, about 80% of the speed of sound, because of the geometry. This is a GE90 turbofan engine. This is the largest turbofan engine created for a commercial jet. It was created for the 777. The Boeing 777 is a jumbo jet. It's one of the largest jets in terms of passenger capacity, but unlike the 747 and the A380, it has two engines as opposed to four. And the reason why Boeing went with this, and airliners like this, is because maintaining two engines, even though these two engines are larger, actually is half the amount of work of maintaining four engines. This generates over 500,000 newtons of force. So with two, you get about 1,000,000 newtons of forward force when these are in full operation. And just to put things in perspective, these engines can generate about twice the power each of all the engines on the Titanic during its maximum thrust. Now, turbofan engines are very efficient for what they do because they're able to pull on the air and push the air behind them. You also get quite a bit of efficiency from a prop airplane because, again, you're actually grabbing onto something and pushing off of that, pushing off the atmosphere. These only operate up to a certain altitude before the internal combustion in the engine fails because you can't get enough oxygen in there. There's some jet engines that are actually designed to fly at even higher altitudes by compressing the air even more, but again, you're pretty much limited by where the atmosphere ends. So to go to higher altitudes, we have to use other means, and of course, the rocket, which contains both the fuel and the oxidizer, is the way that we can actually travel without an atmosphere. Now, the principle here is very, very simple. You're taking a hot gas, you're causing the gas to expand very, very rapidly, and as it expands through the nozzle or bell of the engine, and it's forced downward. There's your action. The reaction is that the rocket goes upward. Okay? So rocket engines, again, can operate in just about any environment. They don't need air. The fuel and the oxidizer are combined. Usually the oxidizer is liquid oxygen, although they've used hydrogen peroxide also. The fuel can be hydrogen, methane, can be kerosene, it's even been alcohol. Again, understanding how the rocket engine works, it's very simple. If you think about the combustion chamber as being the spherical shell where the hot gas is pushing on all sides. By PV equals nRT, the pressure is proportional to the temperature. The higher we can get the temperature of the gas, and the more moles of gas that we have in there, the greater the amount of pressure or force on the walls is going to be. However, the force on this side cancels out with the force on this side. The force on this side cancels with this. The force on this side cancels with this. If we allow some of the hot gas to exhaust downward, there's our action. The gas is being forced this way. The reaction is this force, which is not being canceled out by any other force, because the blue force is not pushing on the walls. The green force will push the rocket upward. Here is a rocket engine. I don't know which one this is. This might be an RS-32. This is in operation on a test platform, and they're measuring the performance of this in operation. The reason why you have this bell right here is we want the gas to expand to atmospheric pressure. Now again, inside the combustion chamber, these pressures are extremely high. So this combustion chamber is actually much, much smaller than the bell of the rocket. So the combustion chamber is right somewhere in here. After it exits there, it goes into this bell. The gas is allowed to expand. We want the gas to reach just about atmospheric pressure. So near sea level, an engine nozzle like this will have a moderate size. You'll see once in space, the engine bells, the rocket bells, get quite large, even though the rocket engines aren't very powerful. That's because they want the gas an opportunity, give the gas an opportunity to expand. Because if you don't have a large enough bell, some of the force will not be directed downward, some of the force will be directed out to the sides, and that'll cancel out and lose some of the thrust. Likewise, if there is too much expansion that takes place, it'll actually pinch the thrust inward. The atmosphere will actually do that, and you'll lose energy through there. So ideally, we want a bell which allows the gas to expand exactly to atmospheric pressure. However, we know the pressure of the atmosphere decreases as we go up with height. And that's why oftentimes we'll use multi-stage rockets in addition to the fact that we can shed some of the excess weight. The rockets which operate very close to sea level, they'll have smaller bells which will be suited for sea level pressure. The upper stages will have larger bells. We see that right now with SpaceX. They just tested a new Raptor engine which is made to operate in space, and its bell is much bigger than the ones for sea level, even though it's really the same engine, just a different bell. The Aerospike engine was an attempt to create an expansion engine where it would expand exactly to atmospheric pressure. But unfortunately, although this produced very efficient thrust at all atmospheric pressures, even in space, the cost of creating this unusual shape and the fact that you actually had to have many combustion chambers operating at once to create this linear spike made it prohibitively expensive, and in fact made it just too heavy to be efficient. It was supposed to go on the X-33, but of course this was canceled because of the cost overruns of the program and the inefficiency of the very heavy engine. Rockets have been around forever. Of course, we know that the first rockets were basically paper wrapping gunpowder. The Chinese invented this, and what they found is if you take gunpowder and just sprinkle it on the table and light it, it just burns like anything else that's flammable. If you completely enclose it in some sort of chamber to allow the pressure to build up, it'll explode. But if you wrap it in a tube like this and allow the exhaust out one end, it creates thrust. This was adapted by Robert Goddard, who figured out that the solid rockets, once you lit them, they were uncontrollable. You couldn't throttle them up, you couldn't throttle them down. Goddard went to liquid fuel and oxidizer, and because of this had a profound effect on the controllability of the rockets and really led to the modern space age. Unfortunately, he did his work in 1926, and the only people who paid attention to it were the Nazis over in Germany. And although it was too late to really have a strategic impact on the war, this led to the development of the V-2 rocket, which was captured by the Allies. And the director of the German program was basically, I wouldn't say forced, but made part of the U.S. space program. And that was Werner von Braun, who was not only the father of the V-2 rocket, but became the principal engineer and director of the Saturn V rocket, the rocket that took us to the moon. So, Goddard had his ideas taken by the Germans, and the Germans' idea for the V-2 rocket, which was an alcohol and liquid oxygen rocket. This was changed to kerosene and liquid oxygen for the lowest stage. The upper stages were hydrogen and oxygen. This is the Saturn V booster. These are F1 engines. These are the most powerful rocket motors ever made. They produce 6.77 million newtons of force. Comparing that to the GE90, these have over 13 times, almost 14 times more force than one of those single engines. 13 of these rockets were actually launched, and again, this remains the most powerful rocket ever operated, even more powerful than the SLS, which is being developed. The problem with the Saturn V rockets is they are obviously very expensive. They're expendable, so once you use them, they fell into the ocean, and that was the end of them. The idea of the shuttle was to create a reusable rocket, and this was thought that it was going to make space travel very inexpensive. The problem is the shuttle had over 1 million moving parts in it, became very complicated, became very expensive, and it actually ended up being more expensive than if we stuck with the original plan of disposable rockets. But this was an important milestone in terms of the reusability of rockets. And of course, we're still using some of the space shuttle's main engines to power the SLS. Again, if you think about this, this is burning hydrogen and oxygen. I should say it's burning hydrogen in an oxygen environment. The action is the hot hydrogen and oxygen, actually it's water is what it's producing, is the superheated steam that's being generated, pushing downward. The reaction is the force that is pushing the rocket upward. And you can see there's a tremendous amount of condensation, that's water vapor being condensed from the air due to the very cold liquid oxygen and liquid hydrogen. The shuttle itself was not powerful enough to get off the ground with its three main engines. Actually needed an assist, and it used solid rocket boosters. And these solid rocket boosters were, obviously more sophisticated than the first gunpowder rockets, but the principle was the same. You'd light them. Once they were lit, they would keep burning. You could gimbal the thrust a little bit, but for the most part, they'd burn for 2 minutes, whether you wanted them to or not. And once they were done, they would detach, and the engine would continue after they came off. The solid rocket boosters generate 13.8 million newtons of force for the shuttle. They've been upsized for the SLS. I'm not sure how much that thrust is. I know it's over 15 million newtons. But again, these three engines were not enough to lift the rocket off. It needed help. The SLS will use 4 shuttle engines and 2 supersized solid rocket boosters. So when we look at the SLS, it's really, and that's the Artemis mission, the next mission to the moon. It's really a combination of what we learned from the Saturn V rocket and the shuttle. Now, chemical engines are limited. Chemicals that are used as oxidizers and fuel tend to be very heavy for the amount of energy that they produce, and therefore chemical rockets have to be very large. Unfortunately, those are about the only types of rockets that we can use within the Earth's atmosphere. Believe it or not, they actually turned a nuclear reactor into a rocket engine, but it was never launched for very obvious reasons. An open nuclear rocket would give off nuclear waste as a byproduct. So unfortunately, that's a very energy-dense way to launch a rocket, but it would be devastating to the environment. Ion engines, however, do not use chemical propellant. You can use solar panels or even a nuclear reactor, closed nuclear reactor, to provide the electricity. And it's not all that different from a chemical rocket. If you think about the chemical rocket, we have the hot gas in the combustion chamber, and it's forced out the back end due to just expansion, PV equals nRT. The temperature gets very high, basically because the chemical reaction converts a lot of chemical energy into thermal energy, and that's the basis for the thrust. Here, we use electrical energy to take heavy ions like xenon and accelerate them through a grid at much higher velocities than the gas would be escaping from a chemical engine, and therefore you need much less propellant. And if you can power them with solar panels, you have unlimited energy. Again, ion engines don't work in the atmosphere. If you turn an ion engine in the atmosphere, the neutral gas molecules at sea level are just going to neutralize the ions before they can even be accelerated, and it won't destroy the engine. The engine just doesn't do anything. Probably just produces ozone and stinks up the place, and that's about it. Deep Space One was the first satellite to employ an ion engine, and this significantly reduced the weight of the propellant and the craft. meaning that it didn't need as large of a rocket to get into space. And Deep Space One was able to visit many asteroids due to this new technology. The other problem with the ion engine is it produces almost no thrust. It produces millinewtons of thrust. Okay? Remember, a newton is basically between a quarter and a fifth of a pound. So this produces, between about 1/45th of a pound of thrust. But because it can remain on for years, this engine remained on for 2 years, that small amount of force, which produces a very tiny acceleration, if you have the time very great, you can get to very, very high velocities. Here's a Space Launch System that we talked about. This has the two larger, they're 20% larger than the Space Shuttle's solid rockets. And then you can see 4 shuttle engines attached to the bottom. Obviously, unlike the shuttle, there's no landing craft that's shaped like a plane. The shuttle would go up like a rocket and land like a plane. Here instead, that's been replaced with a capsule which enters the atmosphere much like the Apollo capsules would. Again, it almost looks like a modified external tank to the shuttle. Down here, you have the 4 engines attached. And again, this, as it is originally configured, will not be reusable. Once these engines are used, they will fall into the ocean with the rest of it and not be recovered. The Orion capsule is reusable, however. And here's another schematic. Core age of SLS will be a liquid oxygen, hydrogen pair of cryogenic tanks. And I'm sorry, did I say RS-32? RS-25 engines. So 4 RS-25 engines. Each engine, produces roughly about 2 million newtons of force. Here is one of the solid rocket boosters being tested, and I'm not sure. This looks like the shorter one for the shuttle. They just tested the SLS booster recently. I think it's a little bit longer than that. Here are future variations of the SLS. Here's it as it is configured to send the Orion spacecraft around the moon without anybody in it. The Block 1B will be the crewed version. It will have a exploration upper stage on it, which I'm not sure if it includes a lander. But you also have a cargo version of it, and the idea is eventually to take us to Mars. We would have to make a few launches to get a transfer vehicle to take us to Mars there, because again, with even the incredible size of this rocket, it's only able to put the Orion vehicle into lunar orbit. Doesn't even have enough to take it to a Mars-type orbit. So the idea would be to launch the transfer stage to one of these larger rockets, and then rendezvous with Orion this way.